All right, so should we get going, Adam? We've got
Let's do it.
I know we've got another couple of folks that will come in. As you see our colleagues arrive, let's definitely get them up on stage. But just to now, Adam, when had you heard about compliance as a thing? EMC, the electromagnetic compliance.
Yeah. So early, but I admit I didn't know what all was involved. I knew that we were building this product, this rack scale computer. We were going to stick it in a thing, and we were going to hope it didn't turn into an antenna. This is the term that I kept on hearing the EEs tell us over and over again, like that it was going to interfere with their AM reception or what. But that was as deep as I understood it, and that was quite a while ago, maybe 2 years ago, if not more. And then at the end of it, we were going to get something that said it was fine and that we could sell it.
The executive summary. Yes. Yeah. And so I think that this is one of these problems. I mean, obviously, we're starting a computer company. We know, and you talk to certainly any of the double E's we talked to early on would kind of shudder when they mentioned, so EMC, electromagnetic compatibility, the EMC compliance, they would kind of shudder, but without real, it was kind of non-specific angst. And I remember hearing that from a bunch of folks. Do you remember when we did On the Metal early on? And we had some of the early folks that worked at Facebook in particular had described the way they kind of circumvented compliance and the way they avoided dealing with this problem.
I don't remember that. How did they circumvent it?
Was that not on the record? Huh. Huh. Now I'm wondering if that was one of these things. Yeah, were we not?
Did you just unseal?
Well, good job, Brian.
Yeah, well, maybe we weren't supposed to talk about that. But so the story about Sweden, is ringing any bells? No. So Amir Michael, sorry, Amir. Okay, so the B-sides, here we are, On the Metal B-sides. So Amir described how Facebook they did not want to do this compatibility testing. I mean, for reasonable reasons. This is not nefarious in that we control the data centers. We're not this is not a product. We control kind of both sides of this. And so we shouldn't need to, these regulations just don't apply to us. And they did some things that were to make sure the regulations didn't apply to them.
Like the motto at Facebook, right? We control both sides of it and the regulations don't apply to us.
I'm pretty sure
to be fair, there are some things you can't measure. And so it is allowed in the standard that you can do what's called site testing, or, basically you bring an antenna out there and you measure your building to make sure your building's not turning into a megawatt transmitter.
Right. You build a big steel box and you put all the things in the big steel box. And you're like, it's fine.
Concrete's very effective as well. But it turns out that if you have a concrete building with windows only up high, you're not going to measure anything because there won't be any.
Right. And it's like their model is kind of like, hey, this is the data center size computer. Like the data center is the product. So the building is the product.
But it's only their product. They're not even selling it.
Right. So this makes sense. This is understandable.
Sure. All these are gray areas that are well defined.
Right. But one of the things that I think Eric, you and Arjen in particular gave me real appreciation for is there are kind of two ways to view this. You can view this as this is this kind of regulatory body and we got to adhere to all these regulations. And that's certainly true. But the spirit of it actually is really, really important. And Eric, I think I can't remember if it was you or Arjen who had the line of if we did not have this regulatory compliance, if people did not need to make sure that their emissions fell within these guidelines, nobody would do it because it's unseen effectively and nothing would work. You would walk into a room and you would have so much bizarre behavior in your life of this appliance only works in this room and doesn't work in that room. And if you move this, and we already have enough of that with Wi-Fi, but it would be much, much worse if everyone were just left to their own devices. Is that a fair summary, Eric?
Absolutely. And what's interesting is the difference between the U.S. and Europe, for instance. The U.S. does not require immunity testing for a lot of things. And immunity testing is, we're going to blast your product with a lot of RF and see if it does anything bad. With bad meaning causes a hazard. And one of those things could be like I make an oven, and the oven turns on when I get a phone call, which is
Right.
something that you can find videos of. Somebody had a
Right.
phone on their stove and it turned on when they
Oh my.
got a phone call, and it's like, oh, that's terrifying. Okay,
Yeah.
all this goes back to, like, back in the days of early radio and TV. You had a lot of interference from random stuff. Like you turn on your blender and your TV would go on the fritz. And then you had the more famous incident on the USS Forrestal, I believe, where basically some unmitigated immunity sensitivity caused some rockets to fire, and the ship nearly sunk, and a lot of people died. And that's all because of the fact that things were not hardened against transients and shocks. And if you've ever been anywhere that has actual winter and gets cold and dry, you know that you need to just be touching something conductive all the time. Otherwise, you're just going to shock the hell out of yourself every time you move.
Oh my God, that is
So-
such a visceral. Eric, I grew up in Denver, but have
Yeah.
basically lived in a more humid climate just the way you describe it, I immediately recoil. Because Adam, I'm not sure you've ever lived in an arid climate like that, where you get so zapped. I mean, you would walk across carpet, and if you weren't careful, yes, you would get absolutely zapped. So yeah, all this stuff is really important, and again, you can kind of view it as unfortunate, but it really is the wrong way to view it. It's really necessary, and it's part of an engineer's responsibility to our kind of broader society, is to make sure that we. I try to remind myself of that whenever we are having a thorny issue that we need to resolve as part of this. So, and Aryan, when you first joined the company too, obviously one of our earliest engineers, and I just remember, as because you're someone who kind of has been on both the software and the hardware side, and just your descriptions of these fields kind of traveling from one they're kind of traveling under advisement. Like, they're not actually with these things that we view as like wires. That's just kind of like advice. That's not necessarily where these things are going to travel, where these fields are actually going to be. And these things are just super, super, super complicated. So I remember we, as we were kind of growing the team, and Eric, you and Nathaniel, and we had a couple of folks that had come from the GE side and had done CTs, and you had done compliance a lot on very big, high current, high voltage kind of things. And I think your line early on was, we will absolutely find things. They will be resolvable, but we will find things. Maybe the place to pick it up is with the pre-compliance that we did. It all blurs together, but I think that was in, when was that? Was that June? I think that was June of 2020.
Yeah, second week of June or first week of June.
That was June in Texas.
In Texas. So
so hot.
It was, and let's maybe describe some of what we did. Like, what does even pre-compliance even mean? What were we trying to? Because the rack is basically coming together for the very first time. So what are we trying to find down there?
So basically, like, there's all these theories and books and whatever you can read on how to design things to not, become big violators of EMC, but the proof's in the pudding, and all those books and examples are usually based on small devices that have fairly simple interconnects. And whenever you get into the real world and have to do large system integration, all that stuff just kind of goes out the window, and everything conflicts each other, and you have to kind of make your best guess of what you're supposed to do. That'll work well for you.
So this is a really important point, because a question that I think has come up, that came up certainly something I had, I think other people have had, is like, wow, we can't simulate this? And the answer is basically no, we can't.
The software companies want you to believe that you can simulate it, and they're like, well, look at this, F-35 simulation, this radome. It's like, you can simulate all the emissions off this thing. It's like, well, sure, if you have an army of 1,000 people and all you do for like 7 years is put every possible detail of your system into this tool and then spend, $1 million computing it, sure, you can simulate some things. It's still not going to be right.
And any kind of errant component can you get one of those details
component. It could be a setting in your component. It could be a batch, a lot, an undefined behavior. I saw one where there were two equivalent parts that could be on a bill of materials for a board. And one of them, when you dead short it, behaved fairly benignly and just kind of turned its output off. The other one kept retrying, and that retrying happened to excite a resonance in the cable that was about 20 meters long. And it just screamed an EMC. And so then some poor person had to go and rework like 300 of these boards to swap out the part, because that part had an undefined short circuit behavior, which was safe, but it wasn't defined in terms of EMC performance. And so we found that randomly on a visit to the chamber. We're like, oh no, what's that? That's awful.
Okay, so in what is the chamber?
It can be even worse. Like you if your supplier comes up with if you basically get a process node change, where you go from a larger silicon process to a smaller silicon process, your edge rate of all your transistors is going to go up, and that by itself may just mean that stuff is going to start radiating because
you'll start getting worse effects from the same board.
Well, and it's just the whole idea that your edges get sharper, and as a result, you actually are now resonating with this component that you weren't resonating with before. And now you have this wholly cascading failure that is actually, there's much more energy involved than just the energy of the part, which is crazy, just because the system is so complicated. So what is the chamber? Let's describe the chamber a little bit.
For any Star Trek fans out there, the chamber looks like a holodeck. And that's a side effect of something inside of it. But basically, it's a giant steel box, and then it has ferrite, which is the material that conducts RF energy fairly well, but is absorbent. It turns it into heat. And then you have this foam on top of that. So it's a steel box, and then it's lined with these ferrite tiles, which are, maybe 100 millimeters aside. Those are all glued to the entire inside surface of this thing. And then inside of that, you have these like pointy or wedge-shaped or some other funky shape carbonized foam. And the carbonized foam is also an EMI, EMC, EMI, RF, whatever term you want, absorber, where radio frequencies will go into it and they will turn into heat. So the whole point of this is to create what's called an anechoic chamber or semi-anechoic chamber, so a SAC. So a SAC is sometimes an acronym that you'll hear EMC chambers called, and SAC just means semi-anechoic chamber. So that means 5 walls of the box are lined with this ferrite foam stuff, and then the bottom is just straight steel, and the steel can reflect radio waves. And so basically the whole point of this chamber is to simulate the conditions of this device that they're testing being out in the middle of space and not having anything around it. So it shields both your device from all external fields, so like the radio transmitter tower that's right down the road, or the FM station, or the cell tower, and also shields your noise that you're creating from getting out of the room. And so the whole point of this is to measure your device in isolation in a perfectly quiet, quote unquote, electrically quiet room, and then measure the very small signals that come off of your device against a standard using an antenna and a turntable, essentially.
Yeah, and so that highlights a bunch of things. So one is that on the one hand, this is simulating, we're trying to keep it quiet around this device so we can understand what this device is actually emitting. It does mean that in principle, you could have two devices that you could combine in ways that could kind of positively reinforce one another. But it's part of the purpose, correct me if I'm wrong, Eric, but it's like the purpose of the standard is like to minimize the odds of that, not to make that impossible. It's not going to be, you can't make that impossible, but
it's a game of statistics. Basically, the whole standard is trying to make it statistically improbable that a combination of arbitrary things in some space is going to cause a problem to something else.
Right. And Adam, if you ever go into one of these chambers, as people will tell you as you walk in, do not bring your cell phone in, because your phone will search for signal and it will not find anything. So your phone will begin to actually drain a lot of battery as it's aggressively not finding. It thinks that you're in space. And
it'll turn up its output power until it's maxed out, and it'll just sit there and happily drain your battery in an hour.
Fantastic. And in this picture, Arjen, that you posted, was that from the pre-compliance, or that was from the actual real deal compliance?
Yeah, that is the run from what is it, 2 weeks ago?
Okay.
yeah, that's a real deal
But that
compliance.
is the actual chamber that we were in for the past couple of weeks.
And so, what did the Texas? Yeah, what did the Texas experiment show us? And what did it look like?
It was a little raw.
Like cowboy chamber? How raw are we talking?
Yes.
No chamber.
Wild West. No chamber. It was an open air. Basically, we were in a back room, which is like the loading dock because the chamber was too small. These are the things you deal with when you have short time and just need to get in there. And so we had basically our rack sitting in a loading dock with nobody quote around it, and then we just manually moved an antenna around it.
Yeah.
Was this useful?
Yeah.
Did we learn stuff from it?
Yes, this was extremely useful. Yeah, I was just going to say. So this was extremely useful, and I mean for so many different reasons. One, I felt it was just like useful for people like me to get education about what this whole thing is and what's involved here. But for us, it was extremely useful. One, we learned some very concrete things we want to get into, but we also, we're also having to bring the whole thing together, and just the process of, I mean, in many ways, like our first customer was in this loading dock in Texas. And we learned a lot. I think we learned, Eric, RFK, Arjen, I think it's fair to say that we learned that we did not want to have to bore holes in the actual product in order to be able to communicate with it. I feel that was one of our big takeaways.
That was a good takeaway. It's funny because wherever I've been, early EMC testing was always like a very big rally point for software integration, because that was kind of generally the first time where like everything had to be working together and be in the hands of non-experts.
Yeah. Yeah, and
a lot of stuff gets figured out.
Gets figured out. And I mean, in pre-compliance, it was great because we figured out a lot of stuff that we had to go do, a bunch of stuff that we knew about, and a bunch of stuff that there's also the stuff that you know about, but the priority becomes much higher in your mind after. And, we had designed this thing with the technician port and the ability to access this thing via the technician port. It was going to be a lot of work to be able to go do that. But coming out of that compliance, we've got to, obviously prioritize that work, and a bunch of folks, Matt Keeter and Aaron and Arjen, a bunch of folks did terrific work, Ben Nacker, on getting all that kind of that whole connection made, and being able to, we learned a lot in pre-compliance just from a product perspective, software perspective. But then Eric, we learned something actually really important from an emissions perspective as well.
Yeah, so we initially found that we were doing both radiated and conducted, and radiated is basically put an antenna nearby and see what you measure. Conducted is put a clamp around basically a current transformer around your power cables or any other cables that come off your device, and see if there's electromagnetic energy on those. And so we saw some on conducted emissions, and we were using an off-the-shelf power shelf essentially with rectifiers that was basically unmodified by us, and we're like, this is weird. What's happening? And so we asked the vendor who makes that, hey, do you have some test reports you could send us? Because we saw something that would cause us to fail. And if you have to do conducted emissions mitigations, radiated emissions is not as nasty because generally the physical modifications are small. Conducted emissions means you have to put some, basically cinder block sized thing of filtering on your power cable, and it gets very scary. Just from lead time.
Our lead time. So these are rectifiers. These are Murata rectifiers. Mm-hmm. We had actually some supply chain issues, and and Adam, I can't remember if I told you this story or not, but there was a moment where we're like, oh God, it's going to be the lead time on rectifiers is so long. Like, how hard can it be to do our own rectifier? And Eric, I just remember you being like, listen, I would like everyone who would like to build their own rectifier to come over here, please. Like, oh God, we're going to learn how to build our own rectifier. And you were just like, I am now going to sit you down and explain why you will never again say we should build our own rectifier. I'm going to explain to you how complicated a rectifier is. Because the question of like, how complicated can a rectifier be? I felt you gave some good answers to that. The answer is extremely complicated. And I mean, you think it's like, the most basic elements are still so fiendishly complicated. And I think we decided that it was a lot easier to help them get the FET that they needed or whatever it was.
Yeah. It was like a rectifier, like a world-class server rectifier is basically like a three-dimensional puzzle filled with complex handmade, hand-designed, like custom components. And all those components are made by a bunch of different suppliers, and they're all very manual in that there's like wires wound, and there's special shapes of ferrites, and there's all these like mechanical and magnetic bits that fit together like this big puzzle. And then you have to also make it EMC compliant, so there's filtering inside of them. And then you also have to make them cheap. And yeah,
right, and efficient too, right? I mean, efficiency is super important.
Yes, extremely efficient. So these things are like insanely efficient, and I hopefully drove the point home that we will not be making our own rectifier anytime soon.
Oh, you drove that! You definitely made us smoke the whole pack. I mean, I definitely was like,
you're gonna light all these cigarettes and you're gonna just start dragging on them.
Right? No, I
don't care if you're coughing. Keep sucking. Let's go.
Right. Well,
so we called Murata. We're like, okay, what are we doing wrong here? Like, you obviously, they have to pass their own emissions, so they're certified independently, whatever. And so they sent us a bunch of test reports from a bunch of different test houses, TUV and Intertech and UL and all these other places. And so I've been on the receiving end of a lot of these reports from sub-tier vendors at my time at GE, and many of them are just kind of like, oh yeah, that's how you tested it. Yeah, okay, that's going to make you look a lot better.
Oh, interesting.
So I've been on the receiving end of really crappy reports where they quote tested it, and it's like, yeah, sure, if it's like this perfect ideal setup, yes, and you have tiny cables or whatever, and just poor measurement techniques or whatever, where it's technically compliant, but they weren't exactly doing their due diligence. The reports I saw from Murata were just phenomenal. Like, everything was beautifully set up as it would be in a rack. The thing was in a like rack style chassis that was sitting on the floor like a rack. It wasn't just, sitting on some foam and, perfectly like whatever. No, it's like, no, there's stuff on here. There's things that would radiate. There's all kinds of stuff. And I saw their data on it, and it's like, okay, yeah, their data doesn't look anything like ours. And then I started looking at the frequencies that they're showing up, because you always see some stuff from the switching power supplies in these things, even if you're well below the limit. And none of those frequencies lined up with any of ours. And so basically the conclusion was, yeah, there was something wrong with that test.
Oh, interesting. Right. Because we were looking at how we were grounding at the chassis at one point, but you felt that the ultimate conclusion of that was just like the test was.
The test was garbage. It was an oopsie, and it's hard to do those kinds of tests because they do pick up a lot of extraneous crap, especially in open air test chambers. And so it's very hard to do that. And I think that was late at night, and we were kind of rushing. And so I don't particularly blame the test house on that one. It's more of just a side effect of we weren't paying enough of attention to say this is right or wrong or otherwise.
But very valuable for us to go in and just even getting their test results and understanding it. I mean, because that was not really something, in hindsight, we should have, but was not something we were looking closely at when we were kind of evaluating these various rectifier folks. But,
right, because they're supposed to meet the standard, but it turns out they have to meet the same standard our whole rack has to meet. So,
and so this is also a really important point. And Adam, I'm not sure, this is definitely something that was not necessarily obvious to me, but the EU, I mean, it should be obvious, I guess, that if you take a bunch of things that are themselves FCC compliant and comply with the relevant regulation and you put them together, the thing that you have doesn't necessarily comply. Like it's
Okay.
actually pretty easy for that to happen.
Yes, it's almost guaranteed.
Right, almost guaranteed.
You
So-
have to meet a higher standard at a system integrator level than the subcomponents have to meet.
Right, because all this stuff also adds up. So you can have
Exactly.
something that's just like, well, yeah, if you had one of these things, it's actually not a problem. But you have 6, or you have 32, or you have 4, and because you've actually added up the actual energy that these things are emitting at this particular frequency, yes, now you're no longer compliant. And sorry for you. So definitely. So yeah, Adam, to answer your question, I thought the pre-compliance. I mean, RFK, Arian, you guys were also there. I felt it was hugely valuable, and we learned just a lot about the product and a lot about what we needed to go do.
It mostly exposed how not ready we were for it, which was, the wake-up call we needed. And we vowed that we wouldn't be so unprepared going into the chamber the next time. And
Yes.
dare I
You
say,
have to
we were
sensitize
better.
people to that. It's hard to do that with words.
Yeah,
It
we
is.
were a little bit better prepared. When not too I won't give us too much credit, but we were a little bit better prepared. Just a hair.
Yeah, I think.
Though, before we move on, Brian, you said we learned not to bore a hole in the product to
Yes.
wire things up. Did we learn that the hard way or the easy way?
Oh no, for sure the hard way. I mean, sorry. I mean, it obviously.
Why did we? Who? Okay.
No, because we
Well, you
had
gotta
to
get
run with
cables
all
out
the
of it.
dongles in. We had
Exactly.
we had no
All the
interfaces
debug
to
adapters.
control the thing. We had all the debug adapters attached to all the systems, so we had to drill holes into the chassis to even get these cables out.
You gotta turn it on,
Love
man.
it. It makes sense.
I mean, you have to like when we put the sleds into the rack. There's a degree to which we've launched this thing into space, and we the things that we are used to dealing with on a bench, we don't have anymore, unless you want to drill a hole in the front of the sidecar, which is what we had to do because it's not that we hadn't thought about this problem. It's just that, to Arian's point about like with the stuff that we still had to build, there was and the connection from the technician port into a gimlet or a sidecar, into a compute sled or a network switch. I mean, it is a crazily complicated path that involved. I mean, like it's not like we were close to having that working. There was a lot of stuff that had to be built. Now we did a terrific job building it over the next, whatever it was, 6 weeks. But it was a lot of stuff that needed to be built.
For folks who haven't seen the sled, there's no like USB or KVM or any of this baloney.
Right.
It's like U.2's out the front and out the back is blind mated power and in Ethernet, like 200 gigabit Ethernet. And that is it. So there's none of the goober ports that you have on your standard server.
And the Ethernet is in a non-standard form factor, so it's really not usable in any way, shape, or form, other than connecting to our exact switch.
And your laptop doesn't have a 100 gig Ethernet port.
Yeah, and this is all plugged into like a fully integrated backplane. So like you've got anything on the front, and there's nothing on the front, and that's it.
Yeah, and now that we built up the infrastructure, it's like that's not really a problem, but back then that was a problem.
It was a problem that could be solved with a drill, and that's what we ended up doing. And I just remember, I mean, just learning a lot. RFK, I was sitting there. We're sitting on that like the kind of the fold up table in this garage, basically learning. Like we've got a lot of work we need to go do to make this thing actually.
I mean,
the
taking
other thing
a 30-minute lap to boot was like the real grinding, very visceral. Like I'm sitting here waiting, watching it boot, and it's just taking forever. You mess up once, oh well, here you go, take a lap.
Weren't we loading the boot ROM out over like 115K baud UART?
This is where we figured out that X modem could be changed, and that was great. That changed a lot. That we went from 30 minutes to 15.
Yeah,
which is a big deal.
So the one thing I will say for pre-compliance testing is it showed us that we weren't screaming our heads off. So the real thing that I wanted to check, like going into that, was that we didn't have anything that was basically visible or off the charts in pre-compliance. Because if it's off the charts in pre-compliance with one sled or two sleds or even three sleds and one sidecar, which is our network switch, it isn't going to get any better when we have 32 sleds and two sidecars.
Right. Yeah.
And so what that did is it told us that, hey, okay, we aren't completely out of bed in terms of being able to get this done, and we don't have like major redesign to do before we get this. There are some things we found that we want to improve, obviously, but those were found later because they were basically so hard to see at that point that they were not visible in the noise.
Right. And I think, this is whenever you're solving a kind of big, hard systems level problem, you do want to get to that things that of potentially unbounded risk you want to get to as quickly as you can. I don't think we could have done pre-compliance any earlier than we did. I think there was plenty of blood on the floor as there was. But I thought, so it was really valuable for that to understand, like, okay, we've got a lot of work to do, but there is nothing that we have got that is obviously a disqualifying from a compliance perspective, I think is the conclusion coming out of that. So
that's what we thought.
That's what we thought. Right, exactly. Well, and then but it was also just very educational and interesting. I mean, Adam, watching this debugging process is super interesting. And, RFK, you kind of came up as an RF engineer. So this is, I kind of felt like you were just like, welcome to like, this is my land. Like, I know this is.
Makes you feel all good. You're all warm and fuzzy for a little bit. And then they're like, go back to designing, differential signaling. And you're like,
feel my pain.
Right. Go back. I know. I think we get, send you back to, I2C translators or whatever. You're just like, no, actually, like this is where I'd like to be, like with the antennas in this chamber, kind of figuring out what's emitting what. So
it's fun.
It was really neat. And it's like these also out of these test facilities, and particularly that one, which was definitely felt like a haunted test facility. I mean, there's just like all of these kind of cadavers of various large equipment kind of lying around. I mean, it's definitely, I feel like a Scooby-Doo mystery should be had in the chamber for sure.
Was the control room also isolated like a Faraday cage?
So it depends on the chamber. So one of the chambers we were in, it is not. Though the chamber that I used to work in was not. It doesn't have to be because everything's shielded and pretty well quiet anyway. Right. So it's just you have big filters to get stuff in and out of the chamber. But the one that we were most recently at does have the control room in and like a little antechamber that is also a Faraday cage, which makes it more obnoxious to be able to test
super inconvenient.
Very I can't take notes on this because all my stuff is disconnected. Great.
And I mean, it has sometimes it's important for that kind of thing, like where you do get some like stray signaling, but like you kind of don't need that.
No,
especially if you got
the only way I've seen that is if you have crappy cables.
Yeah, that's where you would get stuff that would come through. Like we were running, there's Ethernet that runs all the way into the floor of the first chamber, and it comes out of a certain port in the second chamber, and the barrier for that port had been dislodged from the floor, so it was rendered basically useless. And so, now like anything could like potentially come through there, and it's like, all right, well we got the second chamber, and you close that door, and you're like, okay, well we're really solid now. Nothing's gonna just sort of get in. And there were some random things that we saw like once or twice when we didn't shut that door, but generally you don't need to do that.
Yeah, if the chamber's designed right, shouldn't need it. And
I do think, and as some folks are saying in the chat, before leaving Austin, we really do need to mention the barbecue. So CJ Mendez, who's on the Oxide team, who's played an instrumental role in a lot of the logistics and operations of this compliance. CJ lives in Austin, and boy, did he hook us up with the Franklin's is kind of the canonical barbecue in Austin, Adam. And boy, it's canonical for a reason. That brisket was just absolutely something else. That was
it divides Austin into two camps because there's another place that is like half of Austin says Franklin's and the other half says the other place.
And I think they're both right.
I don't care. They're both just
right. I will take them both. Anyway, it was really, really, really good. I kind of felt like it was a little bit of like a Pepe's moment for me.
There you go. Bring it back to New Haven.
Yeah, going to New Haven and being like, Adam has been so insufferable about this pizza that I really don't want. Oh, damn it. This pizza's really, really good. Pizza's actually, damn it, every bit as good as Adam has been saying for the last 2 decades.
There you go.
But as it is with Awesome Barbecue, that was great. Barbecue was terrific. And same, we left pre-compliance with this Murata thing to chase down, and Eric mentioned that we got that kind of chase down, and then a whole bunch of work that we needed to go. We knew we had to go do, not just from a compliance perspective, but just to get the whole product together. And the team really did a terrific job. And so fast forward to December, it feels like it was several years from June to December, but I guess it was only a couple of months. It really does not feel that. Anyway, the time and space have been distorted. So then we were frenetically getting ready for our compliance run, trying to get in. And so it's worth mentioning too, Eric, that these chambers, like, you have to book them a while in advance. These things are a finite resource. And this is not like a Wendy's. You've got to book these things long in advance, and people do cancel, and you can kind of get last minute stuff, but it's a scramble to you can't kind of negotiate your date generally that much.
It's not just the chamber, right? It's the people
3 shifts
as well.
It's both. Yeah, they don't. Yeah, people don't usually run 3 shifts. They'll run 3 shifts if things go long and people are willing to stay. But like at GE, whenever the chamber schedule would open for the next like quarter or 2 quarters, it would be filled within a day with people like staking their claim on it. And then there was all this horse trading and threatening to go to upper management to get priority because we had our own chambers. Oh, there's this whole political like charades and just all this chess maneuvering to get chamber time. But it is a very like precious resource, and these chambers are exceedingly expensive. And so being that we're like operating on short timetables makes it a lot harder, but being flexible, thanks to the folks in Emeryville, and saying, listen, you tell us when to be there and we'll get in, gives you a lot more leverage to get into somewhere because you can adapt to people canceling.
Yeah, and so we were pushing hard for this December date, and that team did. I mean, Eric, you said this earlier. That this is kind of these compliance runs tend to be big rallying points. A huge rallying point for us, pulling together a bunch of different hardware and software. I feel like even though it's not related to the compliance per se, I do feel that it's worth talking about one of the mishaps we had on the way, where we discovered that the shark fin, which is what connects our drives in the front, the U.2 drives they've got a U.2 connector that's connected to a PCI connector, and the shark fin kind of mounts vertically in there. And Josh, I think you were the one who initially tripped over this issue.
At like 3 a.m.
Right. So what were the symptoms of this issue, as you recall?
It didn't work at all, but the lights came on funny, and then they went off funny. I was sitting there like, well, that's funny. These little... I don't think it should come on and then kind of fade out like that. That's not good.
It's not good. And so
nothing worked at all.
Nothing worked at all. And Josh is the one who's kind of been pulling this together from a hardware and software perspective. You kind of hope like, well, maybe I've done something wrong. I don't know. It doesn't feel like I've done something wrong, but maybe hopefully there's some pilot error to be blamed here. But as it turns out, no, you'd done everything correctly. You had encountered an issue that RFK, I think you debugged that next morning.
I don't no longer remember. Oh, this is the part.
Yes.
Yeah, I remember now.
And so
by looking at 2 of them under a microscope, I brought him one of the new ones, and he was looking at one of the old ones and just like doing the dead stupid like, all right, I'm just going to look at every one of these parts and see if they look the same. And he noticed that one was different.
Well, they're like a SOT6, right? They're or SYC5. I can't remember. But anyway, they all look the same, and they've all got very similar part numbering. And our manufacturer just decided to load the wrong reel.
They made a mistake.
Right.
Yeah,
and,
same size part, though.
Yep.
I mean,
totally. Looks the same.
Basically,
almost identical.
Even
basically, right?
Just the wrong logic function.
And
literally
your
the wrong
AOI
logic
won't catch it. Your AOI won't catch it because they'll train on the bad one, and then they go look at all the next ones they build, and they're like, these are fine. No, they're not.
That's the part
Actually,
that's
they're
the
all
part
wrong.
that really feels like a huge process problem to me. It's like, why don't you look at the text that you read in the
Well,
thing?
they do.
They
They do look at the text. There's no like database of like this part has this text on it and blah blah blah. Even if they had that, they would look at it based on the real, because sometimes parts are marked differently depending on the manufacturing site they come from or whatever. And so the typical way of doing this is for prototypes is it's the min for max. It's the minimum amount of effort for maximum amount of benefit. Is they will train it on the first one and then check all the rest of them are the same. And so the question
Which,
is
of course,
whether,
they were.
which they
Right.
were, yes.
Good news.
Which, if they had to
Right.
change reels halfway through, they would have found, hey, these are different, and they would have found it. And in production, you would train it on it, and you would see, oh, these are different, because you'd have a golden board that they can train on. Because it makes it a lot less labor intensive to do that.
But our assumption was not they've stuffed the wrong part. The assumption is, there's so much.
We
else
had the wrong
to be
bomb
broken.
call out or something.
Wrong bomb,
Yeah.
wrong the layout change. This is where we talk about the Eye of Sauron kind of whipping around, and everyone's like going to their own part of the system to understand, like, wait a minute, what's, because we knew quickly that we determined quickly that the Rev C of this particular part worked, and it's the Rev D that didn't, but there hadn't been meaningful changes in Rev D. And anyway, it was the thing that was remarkable to me anyway was, and just what you get kind of undivided attention from such a broad, diverse, and deeply talented group of folks. We got that thing debugged really, really quickly as a team. So that was within 90 minutes, we knew exactly what had happened. And Eric, you took that Nathaniel got these things under the microscope, actually saw, like, wait a minute, this is the wrong part. Fortunately, it should be said, we got lucky. That's the part that was the part of the board Nathaniel was starting on. So he had like the second part. He's like, this one's wrong. And then we had to disassemble all of these racks. So all of the racks had to be disassembled. All of the shark fins had to come out. They all had to go back for rework.
And by all, it was like 500 odd, something like that.
I think I want to say like 1,100, wasn't it? It was.
But we only sent back like 600 something, I think.
I guess that's right. Right. Okay, you're right. I guess there were a couple, but it was.
Which is still, to be fair, it's a lot.
It's a lot.
It's a lot. It
Definitely
is a lot. And
did not regret putting scannable barcodes on them.
Okay. Yeah. So Josh, this is actually a really good point, because this is something. So every FRU that we have in the system, every field replaceable unit, we've got a barcode on there. They're all being scanned in the manufacturer. They're all going into a database. And we had Josh, you had pulled that software together, like kind of moments before this stuff had. And I remember us debating, like, is it worth scanning these or not? And yeah, do you want to talk through that a little bit? Because that was a huge win, I think.
Yeah, we have manufacturing workstations that sit on the line that can scan barcodes. So we have them do that, and then they get programmed into the ROMs that sit on the cards and so on, so that the cards can be self-identifying. And just as an inventory thing, because we're going to send back hundreds of these things, and we have no idea, if we don't scan and log each one that we send out, and also each one that we receive, then there's really no way to know where most of the stock is now that they've come out of the servers that they shipped here in. It's just a lot of parts. And also, we had, if you recall, 20 or 30 of them that I think were not programmed correctly. We wanted to quarantine those on the way back in for inspection. It's just much easier if you have a barcode printed on the thing, and also a cheap and easy barcode reading station.
And this is another one of these things where it's like, I don't think anyone has doubted at the time why this is important, but we're getting an early visceral expression of why this is so important. So, and that was actually, I personally enjoyed. It was definitely a barn raising. I know, Adam, you were in here. A bunch of folks were in here actually.
Can we talk about our child labor practices?
Yeah, absolutely. The child labor was load bearing here.
Yeah.
Yeah, so
you had the whole clan in, right?
I had the whole clan in.
And
I had
Steve too.
The kids were in there, and
they're your children, so it's okay legally.
exactly. Yes, thank you, Josh. Adam refuses to be my lawyer, but Josh is winning.
It's like working on the farm.
It's like working on the farm. Actually, I really liked it. Actually, I thought it was great for the kids to kind of get that physical feeling of like, hey, this is what we're actually doing, and they really enjoyed it. It was so anyway, that was fun. But we were all doing this to get us ready for compliance. So everyone is scrambling hard to get, and we amazingly, when the shark fin thing happened, we're like, there's like compliance is off. There's just no way we can do it. But through this, like, we work 16 different miracles, we pull it off. We're ready for compliance. We are getting there, and we are ready to power on the rack for the first time. And Josh, you were in the room, I believe, when we threw the switch.
Yeah, I took the video of what you're about to describe.
Right. So yeah, what happened? I was traveling for a conference, but I got the immediate after action on this one. I was not in the room when it happened, but
yeah. I mean, we had fully populated the rack, and we turned it on at the wall, and almost half of it did not clear the runway. There were no lights. It was not good.
And you say not clear the runway, you really mean a fire at the end of the runway that includes 14 of the giblets. Yes.
They collided with the seawall. It was not good.
It was not good. It was very bad. So we had 14 of the gimlets. And actually, it was also one of these moments where it's like, it's totally clarifying because there's no question about what happens next.
Compliance is canceled.
Compliance is canceled. Well, no, because I mean, when my now 15-year-old was 4, and he was walking along a concrete planter at a store and tripped and fell backwards. I thought he cracked his skull, but he'd actually broken his arm very badly. Broken his arm very cleanly, I should say. His arm had a giant S curve in it. And as a parent, it was enormously clarifying because it was not like, oh, do I call the advice nurse or, do I call my wife or what do I do? It's like we get in the car and we go to the emergency room. Here we go. That's it. And I feel like this is like, okay, that we know exactly what's going on. We are not going to do compliance. Compliance is not going to happen on Monday. It can't because we don't know what just happened. And we need to figure out what happened. And we've got some hunches, and we'll kind of describe some of those hunches briefly. But I can tell you that what we do know is that Eric and team, Nathaniel and Aaron and RFK were all out here that next week. And Eric, how many power cycles did you guys do of the rack? I mean, a lot of power cycles.
150. It was a lot. And we were power cycling it as abusively as possible because there were many theories between like, okay, well, what if the phase connected first before ground? Because literally, we saw this when somebody plugged the big like twist lock connector, 3-phase twist lock connector into the wall in the other room because
Aaron and I personally executed at least 200 cycles that way.
There you go.
Oh yeah, and I should have taken
of time in the fridge. So
executed cycles is such a fancy way of describing what I saw, which was one of you sitting in one room, yanking the power cord out, and the other one sitting in the other room watching it and pushing a button on your phone to update a counter, like a umpire calling balls and strikes.
It was not interesting.
And the person in the room was just counting in their head. Like, okay, 1, 2, 3, 4, 5. Okay, plug it in.
Well, and it should
try and plug it in abusively.
Well, that's it. We didn't start aggressively because we did not know what had happened. And in particular, we did not know if we power this thing down and power it up, are the other gimlets going to blow? So there was like the first couple of days is being super ginger trying to understand everything. RFK had very quickly pulled the sleds out and very quickly determined that we had blown the FPGA that does the initial power sequencing, the not even the sequencer, but this thing called ignition that Arian that you developed. We knew we had blown that. We did not know why, and this is still a problem that we're causing. We've never seen it again. Our current hypothesis is, and we've got a bunch of, we don't need to go into too much. We can go into kind of arbitrary detail on this, but we don't. Suffice it to say, we spent a lot of time on this problem. But our current hypothesis is that these things were actually blown on the bench. That when we programmed them on the bench, they got blown out on the bench. So when we actually loaded them in, they were dead before we initially powered it on. And we've, as one can imagine, we've made a bunch of process changes to make sure that if this does happen again, we're going to get a lot more information. And meanwhile, we're having the chips themselves, we're having them decapped, so we can understand the actual damage to the FPGAs themselves. We have 14 of them, so we've got, I think actually those just showed up today. So we've got someone who's going to be decapping those and looking at those chips. So we've got a whole bunch of stuff that we went to go explore there. But importantly, one, we haven't seen it again. But secondly, and Eric, it kind of reminds me of the Murata thing, where it's like, on the one hand, there wasn't anything that was due to the testing environment. On the other hand, we learned a lot about Murata by going through the detail, by going into their compliance information. We learned a lot about how these things power on by doing it again and again and again. And Adam, I would say that there was a little bit more art than you implied, in that Eric was doing things deliberately to make these things not power on cleanly. So he was trying to actually, by the end of the week, they're trying to break it and they're unable to.
To the untrained eye, it looked like he was yanking the power cord.
I would get there and like put the thing in just barely, and as cockeyed as it would let me without bending the pins, and like slowly wiggle it in until I started hearing arcing, and then I'd let it sit there for a second, wiggling a little more, and then I'd start moving it in a little more to power up the rest of it. It was trying to be the most abusive thing I could possibly think of, and nothing killed it. We even intentionally disconnected ground and cycled that a few times. That didn't do anything. It's like, it's infuriating when you can't cause a problem to happen again, but it's also good because we power cycled the heck out of it, and it never had a problem. So we're like, well, okay, I guess it's not power cycling.
Yeah, and in particular, we believe that we don't have a design issue on the actual bus bar, the rack. I mean, it would have been, in many ways, would have been satisfying to reproduce it. It would also have been horrifying, because it could have been it could have been a major setback. So anyway, that we get through that. The fact that compliance had been, and this is where just some heroic work by CJ was able to book the time for a chamber in second week of January, right? So we were going in January 7th or something like that, which was was terrific that he'd managed to pull that off. We had everyone here to kind of, there's a lot of software work that still needed to be done. Josh, you were doing a ton of work to actually allow us, because now certainly the concern that we all had is, one, if we were to see this kind of problem again, we want to have information on it, but also just in general, when the rack misbehaved, we wanted to make sure that we were going to be able to actually understand what was going on. So we had a lot of stuff we needed to go build and get integrated, and that was a real lodestar to get all that stuff put together. And Josh, I know you built a lot of software to software that we will then use in the manufacturing line, and helping to flesh out parts of the product for sure. And
already hours before pickup.
Full hours. I'll have you know. Pickup was scheduled for 6 a.m. on Monday, and we were
out of there by 2.
Yeah, exactly.
Pickup was scheduled on Friday.
Pickup was technically scheduled on Friday, and
we may have moved it a few times.
We may have moved it a couple of times.
Steve definitely was like, so when do you think this will be ready? You're like, an hour, 2 hours? And I'm like, 72 hours? He's like, oh dear. Monday then, I guess.
Monday. We should call the Pork Truck Company. Have that moved.
And this is one of these things where it's like, we have the chamber starting at like kind of 9, and we needed this thing to get picked up promptly at 6. CJ was out here in Emeryville when we were getting this thing picked up. So we'd kind of left the off the
large thing. It must be said, it's quite heavy.
It's large.
Not really a convenient physical set of dimensions for something that heavy either.
Over 2,000 pounds.
And it's a cozy fit in the truck.
Yeah, that's one way to put it.
That's one way to put it. Another way to put it is, oh shit, that's not going to fit. That is absolutely not going to. When they were loading that thing, I'm like, there's not a chance that fits. And amazingly, it did fit. They had to pull the door back a little bit to get that thing to fit.
It's pre-squish the foam in the bottom a little, and
right. So we go into the chamber, and what do we discover in the chamber? So we get this, and this is, it should be said, this is not like the kind of the garage testing facility in Austin. The barbecue may be worse in Fremont, but boy, the chamber is much better. So this is a really
the nicest chamber I have ever been in.
Really nice chamber down there. And the thing that was super cool is they got this panel. I should have taken a photo of it. They have a panel, Eric, the thing that you pointed out to me, where you can dial up any country's kind of voltage and phase to test anything. It's like, how's this thing going to do in Japan, or how's it going to do?
Yeah, it's a giant matrix switch of power sources, which is just amazing.
It's really nice. And so that's what, so Aryan dropped. Totally. Like, I'm sorry, which prefecture do you need, Adam, in terms of the
either one, 50 hertz,
exactly
60 hertz, whatever.
Nice.
They don't care.
It really was remarkable, and it's sitting there on, and that's the photo that Aryan has dropped into the chat, where we've got the this thing is on this giant turntable, and now we need to figure out, all right, what do we see, and what are some of the things that we see off the bat?
So we see very little in the low end, which is amazing, because usually power supplies will emit in the like sub 250 megahertz range, and then so we saw like remarkably nothing there essentially. We saw clocks, so we saw some 200, 300 megahertz clocks, some 900 megahertz clocks, a 687 point something clock. So we saw a few clocks, but nothing was too bad if you were a little over the limit. And then we went up into the high frequencies and saw some more clocks and more things like DDR or whatever. But basically, it like I've done EMC testing on large CT medical devices for 15 years or so, and this is the most clean system I've seen go in on a first run. Usually the most impressive one I saw was one where the chamber had to change the scale on the receiver because it was too high. So they had to zoom out so they could measure a higher signal than they were used to seeing.
That's
not
great.
20 megahertz based comb generator from a 20 megahertz clock. That was an impressive one. But
that is impressive.
And like that thing had some particular quirks to it. It had big power and all that stuff, and a big open frame motor. But it was pretty noisy, and this was remarkably not noisy, in spite of the fact that it wasn't like Faraday sealed or whatever. But there were still things that, we failed the first time, and we found some things that we needed to work on and had to go digging into those.
Well, so I in particular, I love the fact. So we have the 687.5 megahertz outlier. Everyone's trying to figure out, okay, what harmonic of what clock is that? One of the things that you'd said is like, well, listen, let's actually make sure we get the rear doors. We've got a cable backplane. It's got rear doors. Let's get the rear doors closed, and let's understand the effect of that. One of the things that is, and we should have a video of you doing this, Eric, because I think it's so fascinating to watch. Adam, this is super physical. So one of the things that Eric wanted is like, I need to be able to see the output. I need to be able to see the kind of the frequency output while I'm manipulating the system. So I want to know, like, if I grab this cable bundle and if I move this cable bundle, like, what do I see with the spikes? If I grab the door this way, how does it change the spikes? It really is, Adam, like, you got the old, like,
antenna.
It's a total antenna. I think this is like a total generational thing. This was like,
tuning the rabbit ears.
Tuning
exactly.
the rabbit. You are absolutely tuning the rabbit ears. Like, no, right there, stand there. No, go back. Exactly, right there. And so, okay, we just need to ship Eric with the rack standing on one leg, just like that, and then we're fine. But one of the things that was interesting was that, so if we close the rear doors, the 687 megahertz 0.5 frequency, like that goes away. That spike goes away. But now there's a new spike at 72, I believe.
All that low frequency that was so clean before got real nasty.
Right.
And it turned out that 72-ish megahertz is about I think it's a half wave resonator with our rear door dimensions. And so our rear door turned into an antenna, which they are wont to do.
They are wont to do. And I think so this is like one of these things, and Nathaniel, you'd use the kind of the analogy of, you've got kind of this ball that you're kind of squishing, the water balloon that you're kind of squishing. If you squish it over here, you're going to get kind of some more water. It's going to kind of come out at a different spot. And this was definitely a very concrete example of that, where it's like, okay, we've done this, but now we've got this other thing that we need to go deal with. And the other kind of thing you highlighted for me is that whenever you see, and Eric, obviously, you've got and RFK and Ariane have got much better kind of intuition for this, but anytime you see any outlier at any frequency, you got to immediately think like, what is that wavelength? And that wavelength is how much, and what does that correspond to? It's like, okay, that is, 9 centimeters. What do we have that's 9 centimeters that this thing could be resonating with? And so in this case,
is it horizontal or vertically polarized? Because that tells you whether it's a horizontal or vertical, the opposite, like opening that it might come out of, or thing that is resonating at the antenna. Because the antenna rotates.
There's a polarization of the wave, and that tells you something about the source that it came from.
So it's a really neat debugging process. I mean, it certainly has a lot in common with debugging that I've been a part of and seen, but it is also like very different. I mean, it's very and it just because it is so physical. But it was so much fun to watch. So us debug that. All right, so we discover we've got some we know that the doors, and then so Eric, you got that coming out of that. We've like, okay, we've got too many emissions, but you've got an idea on the doors in particular. So what was the issue with the doors?
Yeah, the doors weren't grounded along their length intentionally. Like there's a ground strap that you have to have for safety testing, but other than that, there's no requirements for multiple ground points. But if you have multiple connections between the door and back to the rack, it kind of detunes your antenna and it turns it into a higher frequency resonator. And so the hope is that you get enough connection points such that it doesn't look like an antenna to any noise that may be in a frequency that would resonate it, cause it to resonate. And hopefully that doesn't mean that you turned it into a big Faraday cage with like huge copper straps all over and whatever.
Right.
So you don't want to turn it into a complete EMC chamber in itself if you don't have to, because that's expensive.
It's expensive, yeah, and it can be a little bit unsightly. Yeah, exactly, hard to do. Right, we want to avoid that for a bunch of reasons. But so,
yeah, it makes your customers mad too, and your repeatability drops once you ship it in the field, and so then you're, like copper tape is awesome on day one, but like on day 497, it might not be so awesome. So.
It might not.
Yeah, so you got to find gaskets or copper fingers or whatever to be able to make those connections. And the idea is like, okay, let's go in and let's try and make those connections in as many places as we need to get things kind of behaving as they should.
And so this is where, and Adam, I can't remember if we've talked about this before, but those when you pull a drive and you've got those little springy things on the side of the drive that are kind of evenly spaced.
Yeah,
You know what I'm talking about?
Yeah.
So that's for that is for EMC compliance.
No, I didn't know that.
Yeah.
Yep.
That
and they actually
I always assumed that was like, oh, this is to like make it snug.
Yeah, they're exceedingly important.
Yeah, they're supposed to be.
It's for EMC and for ESD protection as well, so that you have a path and you might grab it and not zap it accidentally.
Yeah, but isn't that interesting? I mean,
yeah, wow.
you feel like you've looked at those fingers. I feel like I've seen those fingers for my entire career, and I just drawn the wrong inference about what they're for. It's like, no, this is actually somebody has been in a cage with these, in a chamber with these at some point, and figured out like, oh god damn it, it's we need to go get some fingers in there. Sort of break that up. So yeah, so there are definitely some workarounds to all this stuff. I love coming out of the chamber. The next couple of days, Eric, you were up here in Emeryville, and you were actually grinding off the paint on the. So you were out front. I guess was that what were you using for that? A power tool, obviously. Was that a sander? I'm not sure what that was.
Yeah, I got an angle grinder. Went down
Angle
to
grinder,
Home
there you
Depot.
go.
I'm like, well, we don't have one of these, so I'll go get one and get the old angle grinder out and start grinding away all the metal. And the idea was like, okay, I'm going to grind away everything, so then they don't have to worry about what part of the door is ground versus what isn't. And then, or Robert and the other folks in the chamber can do it more elegantly on the rack itself, so that they don't have to take the thing outside and grind the whole thing with an angle grinder. They can use like a paint scraper or whatever to do surgical modifications of the rack instead of the angry end of the angle grinder.
And then meanwhile, RFK, you were back here in Emeryville just trying to figure out, okay, let me try to figure out some of the things we saw in the chamber. It's obviously noisier, but like, let me see if what I can figure out. And at some point you came up to me as like, what is 2 meters high? And I'm like, what is 2 meters high? You want to describe that a little bit?
The middle of the Sphinx here.
Oh no, it is. And I feel like I feel that like, I mean, we all have, like, I've spent a lot of time in the physical proximity of this rack. And I've spent a lot of time and I'm like, what is 2 meters high? It's too high for kind of a lot of the business in the middle of the rack. It's too high for the switches. It's too high for the rectifiers. And RFK, what is 2 meters high rack?
Well, it turns out that the hinges on the doors are exactly about 2 meters, and the antenna doesn't obviously go lower than a meter. So you really don't. It would presumably also be the bottom hinge. You could probably find the signal strength like very high at that point. But with doors on, really, because you're breaking it up at these 3 points that we had created, the easiest place for it to radiate out of is the top seam of the rack, which would obviously be right at the top of the hinges. And so the peak detection, as you can see in our data, well, we didn't post our data, but in our data, it shows at 2 meters, that is the strongest point of the signal. And, it's a very physical problem that you get to like go and look at the rack and realize in your head. And you have to think about these things that are like just electromagnetic waves that are like, going everywhere. It makes it a more realizable 3D model when you can look at it like that.
Yeah, it was really neat, and I did not guess the hinges. I felt a little bit vindicated when I don't think Steve was guessing the hinges either. I think everyone was struggling to guess the hinges, but it was, of course, in hindsight, makes sense. So we are, and then the other thing that we knew that we had not yet done, that we wanted to go experiment with, is enabling what's called spread spectrum clocking. And do you, Eric, do you want to describe a little bit what SSC is?
Yeah, so spread spectrum clocking is a way of everything in a computer operates off of a clock, which is just a repetitive, synchronous, very controlled oscillation, and that determines what everything does in a computer. So for things like PCI Express, there's a clock that's along with it that is a 100 megahertz clock, and usually that's 100 megahertz, and it's sitting there blasting away at 100 megahertz plus or minus, some handful of ppms. And that's really bad for EMC because that is a very, very sharp meaning very narrow bandwidth spike of energy. And all of the energy of that clock is contained within a very narrow bandwidth. So in EMC, there's a certain opening. It's like how much you open your eyes on the receiver. And they open the receiver up to see about 120 kilohertz, if I remember right, of bandwidth. And that's where they measure the entire spectrum. So if you can make your clocks, if you can spread the frequency of your clocks out more than 120 kilohertz, then the EMC chamber receiver won't measure as much energy at any one point, because basically the chamber receiver is blind to it. And it sounds kind of like cheating, but it's actually it's a reasonable thing to do because a lot of RF receivers have a fairly narrow bandwidth if they're meant to operate at a specific frequency. And so spreading out the energy not only reduces the chamber measurement, but it also reduces the likelihood that you'll interfere with something else.
And so you
because
effectively
you're spreading the energy out.
And you're effectively introducing a little bit of jitter in the clock.
Yes.
Is that correct?
Yeah,
so
it's absolutely controlled jitter.
Right.
So usually jitter is awful in communications.
Right.
But
Right.
more modern, back in the old days, computers didn't have any of this stuff. And if you had spread spectrum, it just wouldn't work. Now computers are designed to have this because it's a quote cheap and easy way for manufacturers to meet emission standards without having to do heroics on enclosures. And so basically you just take the energy that would have been at that one frequency and you smear it across a bunch of frequencies. And
yeah,
so,
I mean, to me, it's like, it's pretty clever. I mean, honestly, because you are, on the one hand, you're introducing something or reintroducing something that we normally try to get out of a system, jitter. But by doing that, you are effectively, you're not dominating this precise frequency. You can actually just move yourself just enough to avoid emitting a bunch of energy. It's not just for the past compliance. I mean, you are emitting less energy at that particular spot. You are less likely to induce resonance in another part or what have you because you're spreading yourself out. So yeah, it's pretty neat. So we knew that we had there is as close followers of the company may recall, there is no bias in our system. We are doing our own lowest level system firmware all the way up with lowest level system software, host boot software. So we are things like spread spectrum clocking, which would normally be either a bias tunable or would happen really, really BIOS. I'm being told that I'm saying bias when I should be saying BIOS. Yes, the basic input output system that dates back to CPM. It was a BIOS tunable, but we're responsible for implementing that ourselves. So we implemented SSC. We did. There's you may have heard us talk about these kind of hidden messages, that these messages that need to be sent to other cores, hidden cores in the computer, and there's a message that you can send effectively on the AMD Milan that says, "I want you to turn on SSC." The good news is that worked great on the Gimlets. The bad news is, Josh, you discovered that when we attach that to the switch, maybe not working so much. It should be said that Josh, like the shark fin issue, ended up once again being on the front lines of like, am I doing something wrong? Like I just integrated this, I pulled in this change and cranked it, and now I'm running it. It's like it seems to work everywhere, but it's not working here on what we call the scrimlets, the gimlets that are immediately attached to the switch, to the sidecar. And Josh, I think that everyone's like, oh well, this must have done something. You must have pulled something in incorrectly. But it's like, nope, we have definitely some a challenge there.
I feel like this is a familiar feeling.
Yes, exactly. So what we learned, and we're still debugging aspects of that issue, but what we definitely learned is that SSC can be enabled on all the compute sleds, and then we need to understand why and how we need to not enable SSC or work around that on these things that are attached to the switch. But actually, this is one of these things where, well, actually, if you can enable it on 30 of the 32, that actually is that's a big difference. So that can actually reduce our emissions quite a bit. And so we wanted to go do that. We wanted to go explore these things with the door. I think what were some of the other things some of the other, I think that those are certainly the two big ones that we wanted to go revalidate when we got back into the chamber.
Well, yeah, there was a bunch of stuff that we did. We looked at. I mean, there was like about a 7-point list of things to do. But when you go into the chamber, you kind of start off with the things that you should start with, like very big changes, and then kind of work as it comes from there, because you'll just find new stuff. So we ended up doing a lot of stuff that was like tangentially related to the list, but not explicitly. Like we know exactly what we need to do when we go in there. That's just I've never like been in that situation in a chamber where it's like, oh yeah, I do all these things and it's perfectly fixed. It's like, no, we went in there for like another 72 hours.
Right. And
definitely.
And it should also
want to understand how each of these things individually behaves and then how they combine, and and some of them you have a little bit more confidence in, some of them you have less confidence in. Some of them we needed to do some physical work, like we needed to scrape off more paint and like put gasket in, and so
Yeah, I mean, yeah,
process.
And also you want to do things. You want to go in there and make changes in ways that your mechanical team will be able to reproduce, and also in a way that will not piss them off when you tell them what you want them to do. Because you can totally be a dick and like make the change really difficult, and they will hate you forever.
Right. So it should also be said that at the same time, we're also doing our safety compliance. And a safety, on the one hand, we're a little bit less concerned about, I would say, because we're not, that there's no reason to believe that we would have major redesign for safety. On the other hand, there's safety is obviously important, and we need to make sure that we don't have, they're going to be testing exposed surfaces and testing for ESD, and there's a bunch of things they're going to be doing. They're going to.
We hit the thing with a sack of doorknobs was the part that really felt. It's like
one doorknob. It's a calibrated doorknob.
It's a calibrated doorknob.
ISO standard doorknob. Is that really safety, or is that masochism? Like what's going on?
The tip test was fun too.
Right, they want to do a tip test, and they're gonna we're gonna do a tip test. And Nathaniel, what were the details on that? They had they want to like tip it over. And they wanted
to. They said we were going to put. Well, yeah, we were going to tip it to 10 degrees, and they said like, oh, just put 2 people behind it to catch it if it tips over. And we were like, whoa, no, that's not happening, because it doesn't look so good if you have to explain to your customer that 2 people died in the process of getting this thing to market.
Well, and
it weighs like 2,300 pounds, right?
Yes. Yeah, it is scary. And certainly if that thing got tipped, it would get very scary. Arian, I loved your line when I went down there to the safety testing house down in Menlo Park. You looked at me just looked me right in the eyes. You're like, for a place dedicated to safety, you can die here. And I was kind of laughing, and you're like, no, I'm serious. Like, watch yourself. I'm like, okay. Actually,
he means you specifically, Brian.
Looks, I mean,
were there fans without guards on them?
And in particular, like the whip that they had us using was definitely like, it was.
The safety testing is not the place where you want people who are not comfortable with working with dangerous things.
Which is like, I guess it makes sense. It's
they're trying to induce failures at some level, and that has inherent risk to it, right?
Yeah. But it was so, I think that Josh, I have to tell you that emotionally, it really did feel like that they were going to drop a sack of doorknobs on it. It's just because we, spent so much time
here in the Ministry of Safety office, like
right, exactly. The Ministry of Safety is going to launch doorknobs against this thing. But it is, as Eric says, it's a very precise test, and we don't anticipate it, or didn't anticipate it. It may cause a facial laceration, but don't anticipate it actually inhibiting the operation of the rack. And then Arian, you guys were also down there doing a bunch of thermal stuff. So
we had to prove that if fans get blocked, that we don't overheat in such a way that components get so hot that you might like burn someone in that bodily harm might occur. So we have to set up some tests for thermal testing, and I'm trying to find the pictures of that because there was some.
It was pretty funny. Because
pretty hilarious. Yeah.
In particular, you are trying to get this thing to overheat, which is now look, we've built a complicated system. We've got a series of trade-offs. We've got a lot of thermal margin in this thing. When one of the very first decisions we made was around the height of so each of these sleds is designed to be tall. It is tall enough, 100 millimeters tall, to contain within it an 80 millimeter fan. It has 6 80 millimeter fans in it. Those fans move a ton of air. They, at very low power, when they're only at 2,000 RPM, they are moving enough air to effectively keep the system cool, unless it's doing an obscene amount of work, in which case they may go up to 3K RPM. The fans themselves can go up to 12K RPM, but they will draw a lot more power. And when Aryan was down there, like trying, I mean, Aryan, you all are trying to like find every intake for this thing because those fans are going to fight you, and they're going to find ways to get air into that thing to cool the CPU.
Yeah, so there's two scenarios in particular we ran. One with the input blocked, so basically the fan is starved from fresh air. I posted photos in the chat. So that's the first one you see with a bunch of cardboard on the front of this thing, and then the second test was where we would block the backside of the rack, and we really tried to close it up, basically to trap hot air afterwards in the rack. And that in particular was kind of funny because we put these cardboard pieces on the inside of the doors, turning the doors effectively into really like wing surfaces effectively. And we started off with a little bit of tape, like the doors were sort of closed with a bit of extra tape to sort of keep them closed. And as the system starts ramping up, because the heat is getting trapped and the fans continue going and going and going, the doors basically get blown open. So we had to put these really like heavy steel plates that are used to take things in and out of the EMC chamber. So we put those against the doors, and then in order to keep the rest, in order to keep those from further tipping and to keep them from sliding, we put a bunch of like heavy weights in front of it, and that was just enough to sort of keep the doors from closing. And then we had to find all the holes by which air was escaping, like the top and the sides, and the thing was definitely fighting us all the way. And in the end, all the hot air would come out on the bottom because that was pretty much the only like real opening that was left, which was allowed for us per the test standards because our rack is expected to stand on a concrete floor or whatever, right. Not on soft bedding, and therefore we don't have to close up the bottom. But if you were to hold your hand on the bottom of the rack as it was running, 15 or 16 kilowatts of hot air coming out the bottom, that was getting pretty warm. Let's put it that way.
Yeah, and the rack can be deceptive because these big fans. They are able to move air without. So the rack is very quiet. If you're accustomed to a data center, one of the first things you will notice physically when you're around the rack is it's much quieter. And you think, is that thing on? And then you go to the back and you just feel this heat just dropping off the back. You're like, okay, no, it's definitely on. There's a lot of heat back here. And you put all that heat in one spot, Aryan. And as you said, I kind of like the idea of the rack on soft bedding, though. I kind of feel like we need to. I guess that's going to be disqualified by our safety compliance. It's not going to allow for a
2-inch shag carpet.
2-inch. Exactly.
Good luck rolling that thing over that shag carpet without ripping up the carpet.
Do you remember when we were rolling it? When we were rolling it into the rack, and the whole rack came to a shuddering stop on a 1.5 millimeter lip on the crate.
Yeah. It's a lot of computers, it turns out. And the other thing that was funny is as Aryan was kind of reporting back from this down to the safety facility, and we're kind of the rest of Oxide is kind of taking bets about this is kind of like thermal margin versus power margin, and we like those fans, if they're all cranked, we will draw a lot more power. And indeed, we ended up for one of those tests, we ended up actually the rectifier ended up actually, sorry, you've reached your limit here, and we designed this thing to go maximum to 19 kW, which is basically what it hit. With the fans absolutely cranking the cubicle, fans doing their job. So that was fun. So safety went, I think broadly, that was largely vindicating, went well. But we need to get back in the chamber, and I'm doing slightly out of order because we did the kind of finish up that safety last week. But then the RFK, you and Aryan had a couple of very late nights in there where you're figuring out exactly how to eliminate some of these spikes.
What is the minimal set of changes we can make in order to pass compliance and not upset our mechanical engineering team?
We went minimal. That's for sure.
What were some of the changes that we had to make, and what was the final result?
So, going back a little bit, we're worried about things becoming antenna, right? And the doors, obviously, antenna, big doors. And as you cut them up, they become different types of antenna. So you can ground them in different ways, and they radiate in different ways, but less, once they're grounded. So that was one change. Definitely make sure that these doors have good ground contact. Okay. But we don't always want to like make people have doors, right? That's not cool. Customers don't want that, especially the front door. And so we're like, all right, well, we can't put the front door on all the time. So let's try to just make sure we don't have to pass and like require our customers to do that. So we put the back doors on. Back doors are fine. And then you do 30 megahertz up to 1 gigahertz. And, once we had done a series of other changes like SSC, there's like potential for some gasketing that we can do in order to like further bring down this like broadband noise that we have. But we can pass without it. Great, cool. Moving into higher frequency. So that's 1 gig up to 8 in our case. And it's 5 times the maximum clock frequency. So that puts us at 8 gigahertz, but we can see all the way up to 18 in our test, so it's like, I don't really care about the rest of this, even though, but we have the data for it. So, we can make improvements later as we like or have time for, which is probably going to be never.
And so where does the standard stop? At what frequency did the standard stop?
Well, it's 5 times the maximum frequency.
Okay, I got you. So it depends on the product. Okay.
Yeah, it depends on the product entirely. So,
interesting. Okay, so once you get beyond the fifth harmonic, they're like, once you get beyond the fifth harmonic, like we just assume that the amount of energy that you have up there is just not going to be material.
Yeah, for that operating frequency that you're running at. And I mean, it changes, and it's like different for different types of products too. So, I mean, obviously there are radios that operate like way higher than that. And then it'll also be dependent upon like how you're transmitting, time on air, like stuff like that. But this is like a whole other class of like problems that we do not have to worry about. Because we do not have intentional radiators and we're not a radio product. So like, yay, good. This would be way worse if it was. Yeah, so we get in and we're working at 1 gig to 8 gig, and what we're going to see, is that the same things that we kind of saw at the low frequency range, the other components that operate with those that are errant are going to be errant in the high frequency range. And lo and behold, all of the drives in the front of the rack scream like none other, because of course they do. It's PCIe, and spread spectrum does a little bit, but not enough. So what happens is we have to try to pass. We don't have the front door on the rack. If you put the front door on the rack, it would keep all that stuff in because we grounded that, but we can't do that. So we're just under the limit for at 8 gigahertz. So we're like, oh, okay, maybe we'll pass. And if these things are not exactly if the clocks shift around, then they'll look for peak detection after they scan once, and it'll try to find like the maximum of the frequency that it found first. And if the clocks move around, obviously like that maximum is going to come down. But if it's something constant, like PCIe clocks, it's not going to go anywhere. Actually, it's going to get worse. Because it's going to go, it finds some local thing that it found, and then it'll search around in that area for the most powerful instance of that signal.
Yeah, and maximize the emission of that signal.
Yeah, because it's just looking around in like all the dimensions that it can to try to find that spot. And so, we had like maybe 1 dB of margin, and it was like, oh man, I don't know if it's going to work. We come back, we go, and we step out of the chamber and let it run, because it takes about 5 minutes to find this. And we come back a little bit later, and oh man, it found it. It sure did. We are so close. I mean, just unbelievably close to the margin, but we passed, so it doesn't matter.
I had some courses like that in college.
Right? It's like we are. I mean, 0.08 dB away from not passing, but we do, and we know the things that will mitigate this in its entirety, which is also the better finding coming out of that. And they don't care. It's like you got to pass, and you know what your solutions are, and you write that up in your report, and then you submit that to the FCC, and that's generally okay. And that is not uncommon for everybody that has to go through and do this. Yeah, and some people have products in field that they'll already have sold it, and then they'll have to go back and do EMC testing, and they'll fail something,
Oh man.
Oh man, then you got to recall all that stuff and go fix a bunch of things. So like, even though we are getting through just barely, like this is way better than like, and especially for the size of the system, like way better
Size
than
the system. Yeah. Well, this is one of the things I think that we really appreciate viscerally in all of this is that that when you have these, when you're selling by the 1U or the 2U, when you're selling kind of the traditional server, it's an easier problem, frankly. I mean, there's just a lot less that's there.
Yeah, just running one of our machines in the chamber, we're passing actually with a pretty decent margin. But if you add up 32 of them, then things become a lot more difficult.
It's a combined effect for sure. And I mean, like no one has to like. I mean, if you're building like a CT or something, sure you're going and, but like that's all one contained system. But we're talking about the rack is like one built up of 32 individual, what should be tested individually things, and like no one goes and does that. Not at this,
but not so much should be, but normally they are individually tested, and they pick their exact sort of test configurations they want to test them in.
Exactly, they'll go pick like they know that like some of these different files are like the worst style for this system that they're going to test, and they'll put that together, and then they'll just say everything after that is okay because they're like, well, this is probably the worst. And then they don't, they just like sign a DOC and they're like, well, we conform with everybody. But they didn't actually test it. No, like we know everything that goes into this rack in the way that it's supposed to. And we're doing it all at once together and it works and we pass. Which is awesome. Yeah, pretty great.
And no one died in a tipping test and we didn't light any.
My thing is like when we shipped this rack down there, I feel like it wheeled out of the box and like it, like 32 machines booted up to Unix and the switches configured themselves and there was just like and then you like hit it with these doorknobs and for some reason it's like it's caught on fire and it's full of shag carpet. Like how is it going to be when it comes back?
It just the thing that's amazing is it just works. Like there's no, oh crap, this one didn't work this time, reboot it. So I'm like, no, it just came up and it worked.
Well, Josh, to answer your question, how is it going to come back? Well, in having gone over many
ground off of it.
No, there's definitely a lot of paint missing. But then, in going in and out of the chamber many times, you had to go over ramps and things. So yeah, the wheels are a little bit squeaky now. So I'm sorry, we may have broken it a little bit.
Yeah, the wheels.
Josh, I kind of share your like, and I think this is how you tell like we really truly do love computers because like, why would you hurt the computer? Don't hurt the computer.
And like the first one that we made too.
Right? It's exactly, but it's
it adds character. That's what it does. When we have it on display in some museum, it will add character.
Rack one, we hardly knew you.
We did well, but I also feel, and Nathaniel, I believe your line was, I don't know that I've ever seen software come together later for something and work as well in the chamber.
Every assignment that I did at university was finished at 2:00 the morning before it was due. So that's just how we roll.
I mean, Eric and I spent a lot of time in EMC chambers over the years, and it's not uncommon for you to have software issues in there, or like in certain systems you want to run them in a mode that like stresses them, and like those are often the like hard modes to be reliable. And so you find like, we ran this test 8 months ago, but like this, no one does this except for an EMC, and so all the bits rotted and it doesn't work again. And so it was really awesome to see the system like show up in there, and it just worked, and it was really nice. Like the team could then focus on the thing they needed to do instead of going and chasing software problems. So kudos to the whole team for that.
We had to tweak it a little bit for like when we started running things. Like one of the things that we hadn't quite anticipated was we had built a stress test for various components, and then we tried to put a load on the SSDs, and we just start the stress test, and basically the entire machine just went out for lunch. Like the thing was just not responsive anymore. It was running, just wasn't making any progress because
it was very busy doing what you asked it to do.
We spun up so many threads per SSD, and that the system was just like done. So we had to.
That's the improved version that wasn't erasing all of its own SSDs.
Yes, that was after we erased a bunch of stuff. Yeah,
sure. we did have it wasn't 2 a.m. Josh, when did that happen?
Well, that's why it took until 2 a.m.
It's why it took until 2 a.m.
like quarter to midnight or like half midnight
Right.
or something, like because we wanted to turn the lights off and do all the lights flashing on the front thing, which
was
did
pretty
work.
cool.
That did happen.
And was cool.
And also it ate all of the partition tables at the same time, which was very sad. Like, don't turn this off
Right.
until we can fix it.
And then Josh back in there with the kludge.2s that we talked about in our small boards. The
jumper cables.
Going in with armed with like kludge.2s in each hand, like you were defibrillating the rack. It was like a combination of like jumper cables and a defibrillator. It was really a great look. As we were going around getting, unfortunately though, we got the rack back on its feet, and we're not going to plow the boot drives anymore. But it was a honestly great effort all around. Really educational. I think over and over again through this journey, we've learned why other folks, because I think a question that we get is like, why are not other people making a rack scale computer? And the answer is like, it's hard, but this is some real concrete detail of why it's hard, is because it is actually hard to get this whole thing together and treat it as a coherent unit. And compliance is, something we had heard a lot about it being a challenge, and it was a challenge, but it was a challenge we were up to, and it was a lot of fun. And I think RK, I love the way you said it about like, we know the next time we go into a chamber, there are a whole bunch of mechanical changes that we're going to be making to make sure that like our margin's not going to be that tight the next time. We're going to get much better margin. And Aryan, I know you were kind of looking at some of the other engineering teams that were down there who'd been teams at much more established companies, and just admiring kind of how they go into compliance. And we've got a lot that we learned. I think we're going to be we're only going to improve over time. But boy, this was a lot of fun, and a lot of work from a lot of folks, a lot of late nights, a lot of third shifts, a lot of early mornings. And a rack that damn near almost didn't fit in its truck. But it was great work all around, and really very important, because without this compliance, we cannot sell a product. So for those folks who've been asking, when are you going to ship? Like, well, you got to actually have the compliance in order to be able to ship. You got to have safety compliance. You got to actually have the FCC compliance. So we are the runway's in sight. Still plenty of challenge ahead as always, but we are looking forward to getting this thing exactly what folks are pointing out in the chat. We are going to ship it as soon as we legally can, and now we've got the legal green light, regulatory green light, and looking forward to getting these things out there.
Technically, we don't have the green light yet. We just have the reports in hand that will get us the green lights, but we still have to defend it. But
fair.
What are you, from the government? Jesus,
yeah.
Exactly.
What a buzzkill.
Oh, God.
If you're a cop, you have to tell us.
It's an FCC deep mole. Yes, we've got to defend it, and we will defend it. That the 0.08 dB.
We absolutely can. We just
this is a discoverable medium.
That's right.
I was talking to Tom yesterday, and it was like, arguing that 0.08 is like getting a D in a class and then having to go to your professor and be like, no, it is worth that 1 point. I get those credit hours.
In the letters S and C, which is satisfactory, no credit for a course you're not taking for a grade. It's the S that's important. But again, terrific work. I know that a lot of startups really struggle with compliance for understandable reasons, because it's expensive and it's laborious and it's a lot of time and energy. But great work all around, and looking forward to getting it out there. Adam, I'm sure this has been, very eye-opening for me. I feel I am never going to look at a product the same way again.
Yeah, see that little FCC sticker on it now means a whole lot more.
Oh, the fact that your TV turns on every time you ask it to? Like most of the time it turns on.
Most of the time.
Yeah.
Most of the time. When it doesn't, it's
a small miracle. Like how well this stuff works on average.
It's amazing. All right, well, hey,
average.
Thanks everyone. Thank you, Eric and Aryan, Nathaniel, RFK. Thank you all of this, and since CJ. Oh, I should actually just in closing, because CJ had to drop. He was listening earlier. He did have some points of clarification that I feel are important. that I had pulled up a moment ago. Let me go pull those up. So on first and foremost, on the actual barbecue, Arian, he believes that the barbecue you're referring to is Micklethwaite. I'm probably mispronouncing that, but in general, just as good. But Franklin's brisket really does live up to the hype. Just be sure to order a couple weeks ahead to skip the line, CJ says. I definitely recommend that. On the number of shark fins, it was 1,136 shark fins total, reworked in 5 days. And as he points out, a huge shout out to Steve for finding a courier for these things who was totally sketchy. That courier was dodgy, but Steve, you did it. They got there and back. And then also CJ says a shout out to Matt Keeter as well for advising him to put more money on the table with EMC chambers in the Bay Area ahead of time. So that really saved our butts on the schedule. So important clarification. CJ was didn't join us up here on stage, but I think everyone here would agree that CJ was absolutely essential on both pre-compliance and compliance. So it really does take a village. And we got
CJ, we appreciate you.
Yes, CJ, legend. Getting those times in the chamber, whoa, shit, that was incredible.
And the Franklins is amazing. All right. Thanks, everyone. We'll talk to you next time.
Thanks, everyone.
Take care.
Cheers.